dinner after this evening, so if you're interested, come and talk to me afterwards.
Well, okay, thanks once again for coming. I guess I'm on. So I've never seen this system before, so I'm not quite sure where it's best for me to stand. Maybe I'll stand right in the middle between the two. Okay, so the purpose of the lecture is to, in a way, discuss the proof of one of the theorems that I mentioned yesterday on counting nodal domains. But the way I really am breaking it up is that today is about sort of the real variable methods or real PDE methods. And tomorrow I want to discuss, you might call it the complex geometry of eigenfunctions. So it's sort of a somewhat new setting to study for sort of strictly pseudo-convex domains and complex analysis. So let's just remember the notation. I'm using the notation lambda squared for, minus lambda squared for the eigenvalue of the Laplacian. The Laplacian is actually a negative operator, so it has negative eigenvalues. And to make that clear, we point out that lambda squared is positive. Then the nodal set of lambda is just the zero set. And if we delete the nodal set from the manifold, it breaks up the manifold into a finite number of nodal domains. The number of nodal domains of the nth eigenfunction in increasing order of the eigenvalue is less than or equal to n. So that's the nodal domain decomposition. So here's some pictures from around 1800. The first pictures ever done of nodal domains. So this is by Chladni, who studied the nodal set and the nodal domains by vibrating the drum. So, all right. Now, here is a kind of overview of what this lecture is. I don't really want to get into details of proofs too much. What I want to do is stress the components of the proof. So the components of the proof seem to me of some independent interest. So although the main purpose in a way is to, that's this one, the main purpose in a way is to sketch the proof that the number of nodal domains, if you look at the number of nodal domains of the jth eigenfunction in an orthonormal basis, we want to prove that the number of these nodal domains tends to infinity as j tends to infinity on a surface with a boundary. So it has non-positive curvature and concave boundary. So this is what is called the Sinai billiard or Lorentz Sinai billiard. On the other hand, I'll prove the same result in a kind of a twin setting where you have a surface, a Riemann surface with negative curvature and an isometric involution. So they're closely related, but the techniques are not necessarily closely related. And in part, the result is based on showing that the eigenfunctions in settings like these never attain the maximum sup norms that eigenfunctions of general Riemannian manifolds are able to obtain. So this is part of a long-term project with Chris Saug, where we tried to understand Riemannian manifolds, which have eigenfunctions which grow at a maximum possible rate in terms of the eigenvalue. So it's nevertheless of some independent interest. It just happens to be applicable to this problem. The second major component in it is what's called quantum ergodic theorems. So this really is hard to do justice to this topic in one lecture. I'm just going to sort of be stating results. But also tomorrow when I do complex analysis, in the complex setting, quantum ergodicity has a kind of new meaning as well. So I'll be describing that in some length tomorrow. So this is this is of course not a surface with concave boundary, but this is an example of a billiard table where I showed this picture yesterday, where when you play, there is no picture online of a surface with a concave boundary. So, in any case, this actually has concave boundary sides here. So the point is that the classical mechanics on this is to play billiards, so it bounces off the sides, bounces off by the law of equal angles, and the billiard ball will have an extremely chaotic motion on a table like this. So we're using this classical ergodicity in order to get lots and lots of zeros and nodal domains for the eigenfunctions. So here I'm sort of going to state the result again. So there are two different settings where we prove this result. The first result takes place on what an algebraic geometer calls a real Riemann surface. So this is a Riemann surface which has an anti-holomorphic involution sigma, where the fixed point set is non-empty. So the fixed point set, think of the sigma as being complex conjugation, and the fixed point set of this involution are the real points of the Riemann surface. And when we say it's non-empty, it means that the real points form a real algebraic curve. And then this Riemann surface is the complexification of that real algebraic curve. Now, so this is really just the setting of real algebraic curves, not necessarily plane curves. Now, there are two different sort of types of real Riemann surfaces. This is a classification that goes back to Felix Klein somewhere in 1880. Namely, one case is where if you delete the real points, you get two connected components. And this case is called the dividing case. So as this sort of indicates, when you delete the real points, you get two surfaces with boundary. And they're glued together along the common boundary. So that's the assumption. That's an assumption on this Riemann surface as a conformal object. Then we're allowed to put any actually non-positively curved sigma invariant metric. So if you take any non-positively curved metric on this surface and you average it under this involution, you take g plus sigma upper star of g over 2, you'll get a sigma invariant metric. So there's a infinite dimensional, there's an open set in the space of invariant metrics which are negatively curved. So there are lots and lots of examples of what's going on. And then the statement is that if you take the even or odd eigenfunctions under the involution, then for almost all of that, for almost the entire sequence, the number of nodal domains tends to infinity. And the same statement is true. You can see that when I take m minus the fixed point set, I get two surfaces with boundary. So this statement generalizes actually to any surface with a concave boundary. This turns out to have geodesic boundary. Always this fixed point set is a union of geodesics of any invariant metric. So the same statement is true in a way in a much more general setting where you take any non-positively curved surface with a concave boundary. The main thing that distinguishes these cases, this is a lot easier to prove than this one. Anytime you're studying Laplacian on a surface with a boundary or a manifold with a boundary, it's very difficult. There aren't very many results. So just to look at the picture, so here's a Riemann surface of genus 2. And if you look at the involution, which interchanges the top and the boundary, then you have a fixed point set, which is this boundary curve. So, okay, that's one example. And here's the formal statement. So, real Riemann surface, the fixed point set is dividing any sigma invariant. It should be negatively curved Riemannian metric. Then what we do is we look at the even subspace. That's the functions which are even under the involution. We look at the odd subspace. And we take an orthonormal basis of eigenfunctions of the Laplacian for the even subspace and one for the odd space. And then for each of the even and odd spaces, we take the limit, the number of nodal domains tends to infinity. So I use phi j for the even eigenfunctions and psi j for the odd eigenfunctions. And for odd eigenfunctions, you have a stronger result. You don't need that the fixed point set divides the surface, just that it's non-empty. Incidentally, this dichotomy, whether it divides the surface or not, is the same dichotomy whether you take the surface and divide by the involution, and in the dividing case it's orientable, and in the non-dividing case it's non-orientable. So this is sort of the origin of the Klein bottle. So let me make some remarks about this even and odd. Naturally, one would like not to use the words even and odd. One just wants to say that if you look at the entire sequence of eigenfunctions, then almost all the nodal domains tends to infinity. However, actually, there's not much difference. So an even function means that if we pull it back under the involution, even respectively odd, we get plus or minus. The even or odd part of an eigenfunction is then defined by this, like sines and cosines. Now, if the multiplicity of an eigenvalue is 1, then automatically the eigenfunction is either even or odd, because this averaging preserves an eigenspace. So if you have multiplicity 1, one of these is 0, one of these is equal to phi j, phi lambda. Now, it's not hard to prove. It's really a very old and standard result in spectral geometry that, in the sense of bare category, if you take a generic invariant metric, then every eigenvalue has multiplicity 1. So for a generic case, all the eigenfunctions are either even or odd. There may be some strange metrics on the surface which have highly multiple eigenvalues, and then our result only applies to even or odd eigenfunctions, not to some linear combination. But nevertheless, that's very, very sparse set of metrics, and generally all the eigenvalues are multiplicity 1. And so we don't really have to make this additional assumption that the eigenfunctions have to be even or odd. It's automatic. All right. So then we have a same result on the C and I billiard. And I just gave an example here. The easiest way to understand this, in fact, the way Sinai and Lorentz originally defined it, just take any non-positively curved Riemann surface and remove a disk from it. More generally, any convex body, any convex domain. Well, and then actually you can remove any number of them, okay, as long as they don't overlap. And then you'll have a surface with a concave boundary. What remains is a surface with a concave boundary. And then here, there's no symmetries, no even odds. Just given any orthonormal basis, you can find a subsequence of density 1 for which the number of nodal domains tends to infinity. So density 1 means that the proportion of the ones that we're discussing tends to 1.
Can it happen that there are examples where the A is your arbitrarily large J where the number is bounded?
With the number of what?
The number of these nodal domains.
So, I mean, there could be a sparse subsequence, you mean?
When does that happen?
I've never seen an example in this setting where it happens. I would doubt it. I think that this is really, this density 1 you need it 3 places in the proof.
I see.
So, there are three places where something funny could happen, but in this field, it's extremely hard to construct examples. You really have to argue fairly abstractly. You can't not write down eigenfunctions except on a standard sphere on a flat torus. Otherwise, that's why we study it, because they're wholly transcendental objects. They cannot really be understood except by theory, or by doing computer pictures. So as I gave this picture yesterday. We read this as removing a hole from a surface. Now, there's an obvious similarity between these two results. It's in some sense really one result in 2 settings. So let me just bring this out a little more clearly and put in some of the notation. So if you look at the fixed point set of an involution, it's analogous to looking at the boundary of a non-positively curved surface with concave boundary. In fact, that, of course, how do you know that? So what we do when we remove the fixed point set, it divides the surface into 2 pieces. We get 2 surfaces with boundary. It's a theorem that any invariant metric, the fixed point set consists of a finite union of closed geodesics, sometimes called the Harnack theorem, although I'm sure it wasn't Harnack who proved it. So, all right. So both cases really are about surfaces of non-positive curvature with concave boundaries. So I'm going to use a standard notation that del sub nu is a unit normal to the boundary, or it could be the fixed point set. And when we talk about a Neumann eigenfunction, then we mean that the normal derivative of the eigenfunction is 0 on the boundary. When we talk about a Dirichlet eigenfunction, we mean the function vanishes on the boundary. So if you were able to glue, like in the real curve case, you're basically gluing the two pieces, two copies together along the fixed point set, and you get one nice analytic surface. That does not work for a general surface with boundary. But an even eigenfunction is Neumann, right? For each piece, because it's even. So when you take the normal, it's non-zero on the fixed point set, but when you take the normal derivative, it becomes odd, and odd things vanish on the fixed point set. An odd eigenfunction is Dirichlet. Odd eigenfunction switches sign under the involution. The fixed point set's fixed under the involution, so the odd eigenfunction is 0 on the boundary. It becomes a Dirichlet eigenfunction. So this is the analogy. Now, here's the main idea of the proof. So first of all, there is a topological part of the argument, which I'm not going to go into very much, a little bit of surface topology. Of course, why do we need an involution or a boundary? Because we're going to relate the number of nodal domains of the eigenfunction to the number of intersections of the nodal set with the boundary. So there's something very special about the zero set along the boundary, or else on the fixed point set. So these curves on the surface are very special, because once a nodal line touches them, it's going to have to kind of come back to them and create a domain. Now, I don't really want to get into the topological part because I have to make a choice of what to speak about. But in some sense, we could be studying the rest of these methods on any curve whatsoever on the surface, and it won't make any difference. All these results would be true, except for the top one. All the results I'm going to be speaking about will be true for any curve you pick. But the only case that I know of at present where you can relate zeros of an eigenfunction on a curve to obtain nodal domains, you need something topological to get nodal domains. So the only cases we know are that basically when the curve is the boundary of the surface. And you can sort of almost guess. You can't really picture this because nodal domains are not necessarily simply connected. But you can sort of imagine that if you have a 0 on the boundary and you start like tracking it into the interior, it's going to come back again and hit the boundary again. Well, it isn't necessarily going to form a nodal domain, but if you have a lot of these things that are coming back, then they're going to be nodal domains trapped in between them. So there's that. Now, that's not a hard argument, by the way. The topological argument's not difficult. I'll say a few words about it. So the key step really, and I think it's a really interesting problem. I'd be really interested to know for people who study complex analysis how they try to do this. Namely, their main problem is really to restrict the eigenfunction to the boundary or to the fixed point set and prove that the restricted eigenfunction has a lot of zeros on it. So for a Neumann eigenfunction, we want to have a lot of zeros on the boundary, respectively the fixed point set. In the case of the Dirichlet boundary condition, of course, it just completely vanishes on the boundary. And that isn't going to give us any good information. So we don't look at the function, we look at the normal derivative of the function if it's Dirichlet. And we try to prove that the normal derivative has a lot of zeros on the boundary. So why should the restriction, an eigenfunction lives on a two-dimensional surface. And even if we know a lot about how it's distributed on a surface and how it oscillates on a surface, when you restrict it to a curve, you don't know what kind of a slice you might be taking. In fact, this problem comes up again tomorrow when I'm going to discuss Grauer tubes of Riemannian manifolds. Really, the fixed point set is the real slice of a complex Riemann surface. And we're going to have lots and lots of zeros on the surface, but how do we know that there are going to be a lot of zeros on the real slice? Somehow, I mean, how can we use the real slice to get lots and lots of zeros? So, I find this a really interesting problem. It's like saying, you know, if you have a holomorphic function on a strip and it has a lot of complex zeros, a very large growth rate of complex zeros, how do you know how many real zeros it has? That's a real slice. So eigenfunctions are real. I mean, the eigenfunction has boundary conditions on the slice, on the fixed point set slash boundary. So it has some kind of boundary. We're inputting some more information about it. It's not just any old function. But there's a lot more to be understood about this kind of question. So anyway, we want to prove that the eigenfunctions, when you restrict them to curves, have a lot of zeros. How are we going to prove that? It's a combination of three kinds of results. First of all, we need to know a priori that on the entire surface, the eigenfunction isn't really very large. And here we use the ergodicity, and we use the concavity of the boundary. Those two dynamical types of input tell you that the eigenfunction is never going to be as large as an eigenfunction can be. So we'll review exactly how large eigenfunctions can be. But, you know, the intuition is that in the ergodic case, an eigenfunction is like a Gaussian random function, like a Gaussian random function. And if you L2 normalize a Gaussian random function of degree lambda, actually its sup norm is of size square root of log lambda. It's really small. So being able to prove that, we're only able to show that it's little o of the maximum possible size that it could have. Okay, so that's one issue. So this is about sup norms. The second issue is about the integrals, what are called periods. We want to integrate the eigenfunction over the boundary or the fixed point set against a test function f. And we're going to show that it decays, almost surely in a certain sense. It decays as the frequency to the power minus 1/2. That's somehow really not obvious. This is really an indication that the eigenfunction, when restricted to the boundary slash fixed point set, is oscillating very fast. Because it's the fast oscillation which is, in some sense, producing this decay rate. This thing is decaying a lot. All right, then the third thing that we want to show is that the square of the eigenfunction tends to 1 in the weak sense. If instead of putting phi in here, I put phi k squared, then you don't get a decay rate. It's going to tend to the average value of f. So this is signaling that this eigenfunction must be oscillating wickedly, because it's not that large. It's like, think about integrating f times sine of k theta. So it's sort of like the Riemann-Lebesgue lemma or something like that. The fast as k goes to infinity, you can integrate by parts and show it's rapidly decaying. We can't integrate it by parts. There's no equation this thing satisfies on the boundary that we can use. But we're going to show in any case that it kind of decays. And this is also like sine of kx. If you take sine squared of kx, then it tends to 1/2. Positive oscillations. Now, why do these three estimates fit together and give you the theorem? So I'm actually relaxing number 1. Instead of showing it goes like lambda j to the minus 1/2, I'm allowing some power of log lambda in there, because it turns out that almost the full sequence of eigenfunctions satisfies this. So this is number one place where we have to maybe subtract or take out a subsequence of density 0. There actually could be some subsequence of the eigenfunctions which is not oscillating rapidly along gamma, and actually you don't get this kind of decay rate for all we know. And I'm sure you can construct examples where that's true. The second one is what's called the quantum ergodicity. If instead of taking phi, we take phi squared, then actually these integrals are big. They tend to the integral of f, so they're big. And the third one is a sup norm estimate. So the numerator, as we'll discuss in a moment, the numerator is the size that an eigenfunction is, the maximum size it can ever be, and then you get a little square root of log lambda improvement. You might be wondering about these logs, why all the logs? And the reason is that all of the dynamical systems that we're talking about are hyperbolic. And that means that the derivative of the geodesic flow grows at an exponential rate. When you get into the proofs of these statements, one way or another, it's the fundamental group of the surface which is growing exponentially fast, or the derivative of the geodesic flow which grows exponentially fast. And the best that we can get is to take times only up to logarithms of eigenvalues. So I don't really have much time to explain that, but I want to point out that this is a famous principle in quantum mechanics. Namely, the time given by the log of the eigenvalue is called the Ehrenfest time. So it was first really realized in the 20s that you cannot understand the relation of classical to quantum mechanics where for a time period longer than like the logarithm of Planck's constant or the logarithm of the eigenvalue. And these kinds of estimates, which nobody has ever been able to improve, these kinds of estimates are the most frustrating thing about the subject, but they are that same indication that we're going to use dynamics of the flow, but we can only use the time up to logarithm of the eigenvalue, up to the Ehrenfest time. That would be a huge breakthrough if anybody was able to push the time beyond the Ehrenfest time. All right, we're going to show that these three inequalities can prove that there have to be an unbounded number of sign changes of the eigenfunction. It has to have the number of zeros of the eigenfunction must tend to infinity with the eigenvalue, and not just that it vanishes, but it vanishes and changes sign at the zero. So, the nodal set could touch the curve tangentially, and then the eigenfunction does not change sign, but we're going to prove that it actually, the nodal set hits it transversely, and the eigenfunction, as you go from one interval along the curve to the other, as you go past the zero, the eigenfunction will change sign. And that's so you have sign changed zeros. So actually, it's because from number one, instead of using a test function f, we can just use the characteristic function of some arc along the curve. The estimate works that way. So I can take any arc at all on the curve, and I want to show that on any arc you have at least a zero. So how do I do that? Well, on the one hand, this thing, this estimate, this period estimate here, gives you this inequality. On the other hand, I'm going to use the most elementary inequality on LP norms. So, namely, the L2 norm means we integrate phi squared. If we integrate phi squared, we pull off 1 power of phi and estimate it by the sup norm. And then we get the L1 norm that remains. So this is just saying that the L2 norm is less than the L1 norm times the sup norm, which is trivial estimate. Now, what do I want to do? I want to show that on this arc, the absolute value of phi is bigger than phi. And that is going to tell me that phi has to have a zero. Because if it didn't have a zero, it would equal its absolute value. All right? So I just use that simple inequality over here. And for the sup norm, I use this estimate. And for the L2 norm, I use this estimate. And I have a different power of the logarithm here and here. So I end up with this lower bound on the L1 norm and this upper bound here. And this one, the lower bound is bigger than the upper bound. There's no contradiction if the eigenfunction is able to vanish on the curve, but we would have a contradiction if the eigenfunction were positive or if the eigenfunction were negative on this arc gamma. So this is a very elementary, naive argument, and you could think about using other LP norms, for example, but we haven't found anything that improves on this simple argument. So that's one place where this could very well be. Oh, so what does this say? This says that no matter how many arcs I dissect my curve, the fixed point set of the boundary into, I always have a 0 on it for large enough eigenvalue. I always have a 0 on any arc for large enough eigenvalue. So that tells you that the number of zeros must be tending to infinity. If the number of zeros were bounded, I would be able to find an arc without zeros, and we know from this that that does not happen. A second remark I want to make is, for sure we can improve this argument with more work to show that at least you have logarithm lambda number of zeros on the curve. That's the least one should expect. Second point is, I would conjecture that the number of zeros of the eigenfunction on this curve is actually of order lambda, which should be huge, because then you get, as it will turn out, we get as many nodal domains as we can produce zeros on this curve. So if we get log lambda zeros, which is a doable theorem, it's just a matter of pushing it, we got log lambda number of nodal domains. If we can get lambda, we get lambda nodal domains, which is a really, really good result. So, these are fast oscillating functions of degree lambda. They should have lambda zeros, but I don't know how to prove that yet. So in the remainder of the talk, I want to go over these two basic analytical ingredients in the proof. And so they have completely independent interest, and you can sort of start over in paying attention to the talk. I'm going to concentrate on them. So the first one is about sup norms of eigenfunctions. Why are your eigenfunctions never of maximal size on non-positively curved surfaces with concave boundary, or on negatively curved surfaces? And the second question is quantum ergodicity. So quantum ergodicity is a big subject, but what it means in our case is ergodicity means that something is oscillating in all directions and in all points in all directions. So quantum ergodicity is the mechanism that's making these things oscillate extremely fast and have a lot of zeros. I guess I wanted to say a word on the topological argument. Just for the sake of completeness, how is it that you're able to get information about number of nodal domains from information on the number of zeros on this curve? How do you do that? So what we're going to do is, of course, there's going to be an Euler characteristic argument. And what we do is, so I'm going to use the notation gamma for either the boundary or the fixed point set. So we're going to turn the nodal set into a CW complex, first of all, into a CW complex. In the odd case, we just use the nodal set. In the even case, we take the nodal set union the curve. In the odd case, the curve is part of the nodal set anyway. And so what we do is, the nodal set, usually consists of a lot of little ovals, and sometimes it has singular points. Every time you see an oval, a circle, add a vertex. Just mark a point in it. Okay. At every singular point, that means a point where the eigenfunction and the gradient of it vanish. Make a vertex at a singular point. In the even case, where gamma is not part of the nodal set, then mark in every intersection point of gamma with the nodal set. These are the zeros along the nodal set. They count as vertices. So, and then put in edges as arcs between the vertices. And that way you're going to get a graph. The nodal set is augmented to give you a graph embedded in the surface. So just as an example, what is the minimum degree of a point of a 0 that's on this curve gamma? Well, you get an edge. See, it's on the gamma, so on the one hand, it has a nodal line coming into it. On the other hand, part of the boundary, it's got an edge coming out of it going on the boundary one way, an edge coming out of it going on the boundary the other way. So it's got degree at least 3. And it's the degrees of those points, the high degrees of those points, which we're eventually going to be using. So just to remind very briefly, maybe I'll just go over this really quickly. What's a graph embedded in a surface? So, you have a finite set of vertices and edges, which are simple, non-self-intersecting curves. 2 distinct edges have at most one endpoint in common. They have no interior points in common, so they're not allowed to intersect except at the vertices. The faces are the connected components when you remove the edges and the vertices. Those are the faces. And you say that an edge is incident to a face if the boundary of the face contains an interior point of the edge lies along the face. Every edge is incident to at least one and at most 2 faces. And if it's incident to F, it's contained in the boundary of the face. We're not assuming that the faces are cells. And we're not assuming that this is a CW complex in 2 dimensions. So nodal sets, unfortunately, are rather complicated from that point of view. But there's an Euler inequality for vertices, edges, faces, when you have an embedded graph. And so here's this Euler inequality, that vertices minus edges plus faces, but then we also subtract the number of connected components of the graph. And so this is greater than or equal to 1 minus twice the genus. So we're going to use this Euler inequality, and therefore we have to use this to get we want a lower bound on the number of faces, because the faces are the nodal domains. Okay? So just very briefly, that the Euler inequality will give a lower bound for the number of nodal domains if you have a lower bound on the number of points where the normal derivative changes sign, in the Dirichlet case, or the number of sign change zeros. So this is why, if you're able to produce a lot of zeros on the boundary or on the fixed point set, then the Euler inequality, just a little arithmetic, is going to give you a lot of faces in that embedded graph. So for an odd eigenfunction, actually it's the singular points, it's the points where the function and its gradient vanish. So odd eigenfunctions, they turn out to have lots of singular points. And we get that the number of nodal domains is greater than or equal to the number of singular points. And for the even ones, or the Neumann ones, the number of nodal domains is greater than or equal to a half the number of zeros along this curve. So anyway, I just wanted to give some indication that we're using the Euler inequality to be able to make a lower bound on the number of nodal domains in terms of a lower bound on the number of singular points in the odd case. That's where the D vanishes. So these are looking at points where D vanishes on the boundary, and or the places in the Neumann case where the function vanishes. Okay, so let me just, having done the topological part, let me just go back and remember what we want. Okay, we just did number 1, relate the number of nodal domains to the number of intersections of the nodal set with the boundary. And now we want to get into the analysis part, the PDE part, where we want to prove that the eigenfunctions have a lot of zeros on the boundary. And this is where we use ergodicity of the geodesic flow. And we also need to discuss the soup norm. So let's start with LP norms. So this is, okay, so we're looking at the eigenvalue problem, and we always normalize the eigenfunctions to have L2 norm equal to 1. So the simplest way to measure the size of an eigenfunction is by its LP norm. I'm interested in the soup norm. So, of course, okay, so this is just a notation. And in case you have multiplicity, the way that we measure the LP norms are to take the LP norm of the largest possible LP norm of an eigenfunction with the given eigenvalue. So I'll sometimes use this notation, but generally I'll just forget that we have possible multiplicities and just assume the multiplicity is 1. But in case it isn't 1, we pick out the eigenfunction with the hugest LP norm. So this is a classical, oh, this should have been divided by 2. All right, sorry. So there's a universal upper bound on sup norms of eigenfunctions which are L2 normalized. So this is a result. It should say that the sup norm of the eigenfunction is bounded by a constant times lambda to the dimension minus 1 over 2. So this is true for every eigenfunction and with a coefficient depending just on the metric. So this is a kind of interesting a result for analysts in the audience because it's really a hyperbolic estimate. It's an estimate that you can prove using the wave equation. You know, in PDE, people like to prove the sup norm estimate maybe by using Sobolev inequality or Moser inequality or something, and you'll never get this sharp an estimate. So I should have said the square here, or else I divide this by 2. So sorry about that. So it actually is sharp. So well, I don't maybe want to state this, but these are SOG has generalized these kinds of results to all LP norms. So maybe I will skip this for the moment, except to point out that there's one range of P's for which you get a certain type of upper bound, and then there's a kind of phase transition in LP norms at this critical index, twice the dimension plus 1 over dimension minus 1. And I guess I'm just going to be showing some pictures. So I think of it as high LP norms and low LP norms, and there's somewhat different geometry in the different cases. So all these LP norm estimates are actually achieved on the round sphere by certain special spherical harmonics. So for high LP norms, the rotationally invariant spherical harmonics saturate them. So this is very similar to Bergman kernel. So it's the same sort of thing if you fix one slot of the Bergman kernel and take the LP norm or sup norm of the other slot. It's exactly that kind of object. So, but on a surface of revolution, you also have eigenfunctions which attain the maximum possible, which on a surface is lambda to the 1/2. So anyway, surface of revolution and a standard sphere saturate the universal bounds. For low LP norms, it's really not known what the geometry of the eigenfunctions is. It's known that what are called Gaussian beams, which are kind of like Gaussian functions transverse to a geodesic. So I'll show you a picture in a moment, but what are called Gaussian beams along stable elliptic geodesics, they saturate the low LP norm inequalities. So here's a picture. Number 1, this picture over here is what's the zonal spherical harmonic over here. So it's a rotationally invariant eigenfunction. It looks like some of the pictures yesterday of the hydrogen atom. It has a peak point at the North Pole. It has a peak point at the South Pole. In fact, these things are either even or odd functions under x goes to minus x. So if it peaks at the North Pole, it must peak at the South Pole. And if the degree of the spherical harmonic is n, then the size of the eigenfunction at the pole is the square root of n. So this is achieving the sup norm bounds, the universal sup norm bounds. On this side, this is harder to draw, but if you look at the equator of the sphere right here, then along the equator, a Gaussian beam is like a rapidly oscillating function along the equator. So it's very large along the equator, but not at all as large as the fourth root of n along the equator. It's much smaller than the peak points here, so it doesn't maximize sup norms. But it maximizes the L6 norm, for example, or the L4 norm, because although it's smaller, its top size is smaller than this one, it's large on a much larger set. So this one, and like Bergman kernels, for people who know about Bergman kernels, this is really huge, but on a very, very small measure set. And this one is much smaller, but it's large on a larger set. So it maximizes, you know, a very high LP norm gives you a lot of credit for being big at one point. A low LP norm, you have to be big on a fairly large set. Okay, so, all right. So here's just another graph of these things. These are these examples of these zonal spherical harmonics. Well, anyway, so you can see the different sort of shapes, and this one obviously is bulging out at the North Pole and South Pole. So, you know, these inequalities are the inequalities which are the worst possible things. They're the extremal problems for eigenfunctions. And not every Riemannian manifold has eigenfunctions which achieve the maximum possible LP norms. And for short, Sog and I say that, that the eigenfunctions have maximal LP growth if you can find a subsequence of eigenfunctions which saturates the LP bounds. So here's a kind of a theorem, or we're aiming at a theorem which tells us exactly when you have eigenfunctions which obtain the maximal sup norm bounds. So we notice that in the case of the zonal spherical harmonic, the thing bulged out at the poles. And it also was true at a surface of revolution. What's a pole? Well, one thing a pole is that every geodesic that leaves a pole returns to the pole at a given time. So we actually will call that in general a self-focal point, because to be a pole, the geodesic has to return to the initial point and smoothly close up as a smoothly closed geodesic. But it's possible also for all the geodesics to leave a point and then return to the point and make a loop, which is not a smoothly closed geodesic. So I'll call a pole one where they're smoothly closed, and I'll just call it self-focal or blowdown for some reason if they just loop back. So surface of revolution, standard sphere, these are examples where you have poles. You have points where all the geodesics come back smoothly closed. You may or may not know that if you have an ellipsoid has these other type of points called umbilic points where all the geodesics loop back. So here's a picture of a surface which has a pole. And here's the surface, the ellipsoid. These umbilic points here have the property that every geodesic leaving an umbilic point returns to the umbilic point at time 2 pi. But it returns with a twist. It does not return as a closed geodesic. It comes back and makes an angle to itself. So this one is self-focal but not pole. This one's a pole. So the only known examples of Riemannian manifolds which do have a maximal eigenfunction growth are manifolds which have poles. So as I'll state in the next slide, Sog and I recently proved that this must happen for real analytic surfaces. The only possible time when you achieve maximal sup norm growth for high LP norms is when you have a pole. Okay, in fact, more likely, most of those guys do not have maximal eigenfunction growth, but that's the status at the moment. And the only known examples of eigenfunctions saturating the low LP norms are Gaussian beams of Bowling elliptic closed geodesics. But this is a wide open statement. Nobody has any real technique for trying to prove this right now. So many years ago, Sog and I proved that if you have any smooth Riemannian manifold which saturates the top LP norm bounds, so that means that it achieves this inequality, then there has to be a point for which the set of loops at that point has positive measure. So, you know, one thing, by the way, is that you think smooth metrics are really simple, but actually, as soon as we leave the world of real analytic and move into smooth, it's actually very difficult. So all we can prove is there's a positive measure of directions which loop back. Okay? So in the real analytic case, just very recently, we proved that if you have a real analytic surface without boundary and with maximal eigenfunction growth, then, in other words, achieving this maximal supernorm bound, then there must exist a pole on the surface. That means a point where every geodesic through X is a closed geodesic. So M must be a topological sphere, and the metric has the property that there's a point on it, and every geodesic through that point is a closed geodesic. We've also proved the following thing. So this is kind of about a surface with boundary, which is much more difficult, because when you have a surface with boundary, then you have to confront diffraction theory. And diffraction theory is a very little known, very little studied part of PDE. So using a lot of the Melrose-Taylor diffraction theory, we proved that if you have a smooth, non-positively curved surface with concave boundary, then at least along the boundary, the eigenfunction and its normalized normal derivative are always little o of this maximal of this possible maximal exponent. So, for example, on an equator, on the northern hemisphere, which is a geodesic boundary, in fact, the zonal spherical harmonic is either going to be Dirichlet or Neumann. So, in the case of a sphere where in the northern hemisphere you do achieve maximal supernorm growth, but we're saying non-positively curved with a concave boundary. So it's the non-positive curvature which is going to rule out ever having eigenfunctions where along the boundary they achieve maximal size. And maybe I think I will skip this slide, but there's a result in higher dimensions. And I might point out that this gives rise to two geometry problems of a kind of geometry which I guess people don't really study very much anymore. Number one, I don't know a single example of a three-dimensional manifold or higher which has a point where all the geodesics return unless they come back smoothly closed. So an ellipsoid was an example in 2 dimensions where every geodesic loops back, but they're not smoothly closed. There's an angle in general between the initial and terminal directions. That does not work for higher dimensional ellipsoids. It doesn't have that. So I don't know a single example of a Riemannian manifold of dimension higher than 3 which has that property. And that would be a big help to us if we could prove they did not exist, because this kind of behavior is an enemy for our theorems. Another one is that in order to prove that you don't just have loops, but you actually have smoothly closed geodesics, in 2 dimensions we use the fact that sort of the first return map on the unitangent sphere at that point is a reversible diffeomorphism. It's conjugate to its inverse. And we prove that it preserves an L1 measure on the unit sphere bundle. In dimension 2, we can prove that forces F to be a very simple-minded map. It squares the identity. We had to use rotation number. For example, with this property, the rotation number was either going to, if it's reversible, it's either 0 or pi. And then we can play with the fixed points to be able to prove that the square of the map has to be the identity. I don't know if there's any such possibility in higher dimensions. So we're very interested in the theorem in all dimensions. So the last ingredient that I want to mention just at the end of the talk is how we use ergodicity. So remember, we want to prove you have on every arc, we want to prove that the eigenfunction or its normal derivative has a 0 where it changes sign. And we do that by showing that the integral over the arc of the function has a different order of magnitude from the integral of its absolute value. So in order to do that, we prove that the integral of the square of the function is huge, although the integral of the function itself is decaying. By huge, I just mean it's 1. It's just not decaying as the eigenvalue goes to infinity. So here's the theorem we use. This was a theorem which, to some extent, we proved it for this purpose. So Andrew Hassel and I proved this from the boundary case about 15 years ago. And Christensen, Toth, and I proved it in every case just last year. So the statement is, without getting into too much technicalities, in the Neumann case, if you just take f, you take the eigenfunctions and you restrict them. Here gamma is either the boundary or it's the fixed point set. And these are restricting eigenfunctions to that set. And we want to see if the square of the eigenfunction, when it's restricted, oscillate. It's a positive function, but we want to see if it oscillates so much that it smears out to an average value. And this theorem says it does. So again, for a subsequence of density 1, this is just the integral of f against the square of the eigenfunction over the fixed point set or over the boundary. And it says that along a subsequence of density 1, this tends to the average value, essentially the average value of the function f along that curve. So quantum ergodicity itself is the statement that this kind of behavior holds on the whole manifold M. And once again, it's like if the fact that f times the square of the eigenfunction, it says that the square of the eigenfunction is tending to 1 weakly in the sense of measures. The fact that it tends to 1 weakly on the whole manifold doesn't give you any evidence at all that it should tend to 1 on a curve on the manifold. So this is, this is one of the big inputs that we use. And just exactly the same statement that in the case without the boundary, we have this for the even eigenfunction and similarly for the odd ones. And I think maybe I just mentioned that this is part of a very general theorem. You can pick any hypersurface whatsoever. And what the general theorem is that the Cauchy data of eigenfunctions has this ergodic property along the hypersurface. And it's the quantum analog of the fact that when you have a geodesic flow and you create a symplectic transversal to it, it remains the first return map is ergodic. So this is kind of a quantum analog of taking a symplectic transversal to a flow, and it turns out Cauchy data of eigenfunctions is kind of a quantum analog of taking a symplectic transversal to a flow. So that's where I'll stop. Yes.
It's a period estimate.
Pardon me?
Period estimate.
Yeah. So period, that goes way, way back. So I did not explain that at all. So the period estimate, wherever it went, over here. So this is the period estimate. It just means that if you integrate the eigenfunction over this boundary, but you can put any test function in here, then it decays at this rate. So that's related to what in automorphic forms is called the Kuznetsov formula. So many, many years ago, I generalized the general Kuznetsov formula for automorphic forms to any Riemannian manifold. And so this is, then actually with Hassel, we kind of gave a new insight into this theorem just last year also. So it's a separate issue, but actually somewhat easier, I would say, than the other ones.
Condition appears in the quantum ergodicity result.
Yeah.
What are other places?
Well, yeah. So what's going on? In general, you cannot understand an individual eigenfunction, or it's very hard to understand an individual eigenfunction. So the way that you understand them is by doing sums over eigenvalues. However, doing sums over eigenvalues allows cancellations between terms. So in fact, what you try to do is average positive quantities. So the basic, it's really the following argument. So as you well know, when you want to prove weak mixing, you use exactly that same kind of argument where you sum a positive quantity and you prove with a subsequence of density 1 that something happens. So it's exactly that kind of argument where you do spectral averages, but you do spectral averages of positive quantities. So in quantum ergodicity, the positive quantity that you do is that you take the left-hand side, you subtract the right-hand side, and you square it. And you have to do that. So, or you can actually take any convex function, or the left minus the right-hand side. Even an exponential function gives interesting information. So that's how you prove this. But when you average positive quantities and the average goes to 0, it doesn't tell you that every single thing goes to 0. It just tells you almost all the terms have to go to 0. In this case, we take the period and we square it, and we average it, and same type of thing. So, yeah, that's a technique. In other papers, we do L4 norms or something like that. But in general, when you do these functions of these things, it's really no obvious reason why the spectral average should have any asymptotics at all. It's not classical type of spectral asymptotics. If you take like left side minus the right side, square it, you're not going to see any kind of standard asymptotics for it. You need something, some kind of dynamics to be able to get an answer.
Thank you very much.